Hi guys, so today I'm presenting on back propagation and tips and tricks for NN2. So my first tip is to create an NN class, because of course it gives you a nice place to put feed forward, back propagate, and modify functions, but it also gives you the ability to have multiple neural networks at once, without worrying about data that they share being modified. So if you would think about a system without class structure, you could accidentally change a variable that the first neural network needs, and then have it affect the second neural network, if they're both referring or looking for the same variable. So this gives you a very nice self-contained way to keep your neural networks separate, but still allow them to have functions that let them perform. So another thing that I thought was very beneficial when doing this lab is asking questions. So what is learning rate? That's one of the questions I had. And should it remain constant? What effects does it have on learning time and accuracy? So I just thought about what learning rate means and where it's used after the negative gradient is found. And what I came up with was that it's like taking steps. So if you want to take baby steps, you have a small learning rate. So then it comes down to the question, do you want to take big steps or small steps? And the answer depends on how far you are along your training process. So this is not totally required, but for me, I thought about it as maybe creating a function. So after a certain number of epochs, your learning rate becomes smaller. So you can start to tweak and take baby steps instead of big steps forward and then having to take smaller steps backward. Then I also thought about, am I using recursion or iteration? There isn't necessarily a good or bad answer here, but it's important to know what you're doing while you're coding. So for me, recursion came naturally when I was looking at feed forward, and iteration was more natural for back propagate because back propagate involved a lot of numbers, and it's hard to see that recursively. But again, either option will work. It's just a matter of what is more natural to you. Also, I thought about the question of how do I handle bad random values, and my answer to that is creating a pool. So this, although it requires a little bit of space and time investment at the beginning, it significantly decreases runtime in the long run, because what you're doing is you create a pool of 20 neural networks, so they all have random values and they're all different. And then you run one single epoch, so you train it on the entire dataset one time, and you see which one has the least error, which one is the best and can move forward. Then you only use that and then do back propagation and just regular training. So this basically eliminates the chance of having a one-off bad random value neural network. So this fixes that problem. So looking at class structure, I had 3 functions and 1 constructor, and so my constructor just took an input size, and it created a self.structure variable, which basically has all the nodes in each layer. So the first layer should have input size plus 1 for the DC offset. Then we have self.alpha, which is just equal to your learning rate. So my learning rate was 0.1 for NN2. Self.weights, that is basically what you're going to use to fill in all the weights in your neural network, and we'll talk about how to calculate how many weights you'll have at the end later on. But just think about it as some random stuff, so some randomly generated things times some stuff. So how much ever big your layer is, and you're doing that so that you can fill in your weights and you know what to multiply by what later on. So then you have feed forward, and since you're going to be doing like nn.feed forward, you have to include self, and this also gives you access to self variables. And so you do self, last layer, weight stack, and trans. So last layer is just the last layer that you process. So since I was doing this recursively, that's how I thought of it. Then weight stack is the weights but flipped, so you can just pop off the stack. Then trans is your transfer function, and in this case sigmoid. So you can define sigmoid outside as a global variable, and I can talk about how to do that with a lambda function later on. Then we have def bp, which is back propagate, again self. Imp, which is input, expected out, and actual out. So you're going to use that to calculate the negative gradient, and then modify self will let you actually change the neural network given the negative gradient. Some more tips. Don't hard code your architecture into your neural network. Just leave things as variables, and you can change them as needed. So for example, don't make your feed forward function only work when there's 4 layers. Make it generalized. This lets you not only like play and experiment with your neural network later on, but it's also good coding practice because you want other people to be able to understand what's going on and know that your code will work in multiple situations. Then one other tip is to try to use list comprehensions and lambdas where they work. So for one, they can make your code more visually appealing by making your code shorter and easier to read. But actually, list comprehensions offer a slight speed advantage because the Python interpreter is able to see patterns. So it's able to see that there's a list comprehension, and that actually reduces the number, how long it'll take to run, because it's able to recognize that pattern. And although lambda functions don't actually reduce runtime, they are a mechanism that helps you create a function or create a function faster, and it also is more readable. I'll show that on the next slide, but lambda functions are highly recommended. So here we go. So the name of the function, my function, equals lambda, which is just, again, the mechanism to create a function. The end result here is still a function object. The input variable, or variables, so you can do lambda x comma y if you want multiple variable inputs. So lambda x, colon, then you have what actually is performed, so x cubed. So that gives you the ability to create a function that cubes a number in one line. And so if we extrapolate this to what we're working with, we can create a sigmoid function t3, as you see in one line. T3 equals lambda x, colon, 1 over 1 plus math.e times negative x. So that gives you 1 over 1 plus e to the power negative x. And so all you need to do there to use it is t3 parentheses, whatever your input x value is, and that'll output your sigmoid activation value. We can also do this for t3 prime and t3 prime after. So in our case, it's most likely that you want to use t3 prime after because you are already having your input be the y value. So your input to t3 prime after should already be the activated layer, and that's likely what you're going to see in your code. Now we can move on to training algorithm. So the training algorithm is it's just a set of for loops, and here I've provided some pseudocode for that. So nn, lowercase, because I don't want to make it confusing, equals uppercase nn, so that's my object, and the input is the size of the input. So my lowercase nn creates an nn object. Then for each time in epoch, so for how many ever epochs, I think I did 250,000. You can change that depending on how fast your code runs. And the sum of errors equals 10 times line of dataset. So there are multiple ways to implement this. If you would want to, you can do sum of errors equals just an empty list and append to that every time in the loop below. And then we start a new loop inside the outer for loop. And this is for each case and dataset. So your dataset should be 4 or 5 things maybe for this lab. It's not a very large dataset, but you can think of each case as, for example, 101, output is 0, so that's one case. So then we have outputs equals nn.ff case. So nn is your object from earlier. Then you use ff to feed forward your case. So you're feeding forward whatever case you're on in your dataset. Then you find the negative gradient using back propagate. Then you use nn.modify to modify the weights of your nn. So the nn object is actually being changed here. Then we can do sum of errors of index equals whatever error you produced from doing your back propagation. So again, this is pseudocode, so you can't just copy paste this, you have to change some stuff. And you have to understand where the numbers are coming from. Yeah, so after you're done with one cycle of your dataset, you now have your sum of errors, and you can sum up 1/2 times error squared as the error equation goes. And if your sum of errors is less than the desired error sum, your error is low, and you are done with that test case. So you can break, and that's when you can have your print statements for the lab. So some applications and extensions of NN2. NNs are very powerful. Neural networks can do a lot of things, so you can try some cool new projects. For me, I was already familiar with the MNIST dataset, so I just modified my NN2 to have 10 nodes in the output layer, and that means I was able to train digit recognition using, again, MNIST, and I could get 98% accuracy on the first 1,000 MNIST images within 20 minutes of training. So, as you can see on the bottom left, those are MNIST images, and they're really just pixels of size 784. So you have 784 pixels, and that forms that image of 0, 1, 2, 3, 4, or up to 9. And so the input is 28 times 28, which is 784, plus 1 for DC offset. Then it had a second layer with size 128, a third layer with size 20, and a last final layer, or output layer, with size 10. And so, in this case, I was curious, how big would my neural network be? So to calculate the total number of weights, you just multiply each layer by the layer after it, and then add them all at the end. So 785 times 128 plus 128 times 20 plus 20 times 10, and that ends up giving you 103,240. So that's how many nodes I had, and that's what enabled me to recognize these digits. Also, one important thing to know here is that the index corresponding to the highest value in the output layer is treated as the answer. So this sort of resembles something called softmax. You don't have to worry about it for now, but the idea is that we're not just taking one node at the output, we're taking 10, and then we're picking the highest value there. So if we see a bunch of 3s and then like the fourth index is a 5, then 4 is the answer from the neural network that we can interpret. So some cool stuff to research beyond the material in so far that we covered so far is layer dropout, which is basically killing nodes. So if you want to think about neural networks as biomimicry, which is really just mimicking a process that you see in nature, neural networks are like brains. So believe it or not, brains have neurons that fail all the time. And surprisingly, that can actually benefit your neural network by decreasing train time and increasing accuracy. And so it's been found with MNIST, for example, killing off nodes actually has the ability to affect your output in a good way. Also, we have different activation functions like tanh, ReLU, leaky ReLU, and there are many more. But the most popular, I'd say, is ReLU because its derivatives are really easy to calculate. So if your input to the derivative of ReLU is less than 0, then your derivative is 0. If your input is greater than 0, then your derivative is just 1, so it's really easy to implement. Also, you can try different network sizes, so more layers, more nodes. I tried it with MNIST. I tried having 5 layers and basically adding a layer with 40 nodes, and it wasn't really beneficial, it just took longer to run, so adding layers may not always be the best move. Pruning. Pruning basically gets rid of useless parts of your neural network. You can vaguely think about it as alpha-beta. So in an alpha-beta recursion tree, you cut off parts that you know are not going to have the answer. Similarly, in a neural network, you can, as you're propagating forward, you can cut off parts that you know are useless. And that enables you to have less runtime because you don't have to evaluate all those nodes. Also, there are multiple types of neural networks that we so far haven't covered, including convolutional neural networks, recurrent neural networks, and many more. So convolutional neural networks enable image analysis by like convolving and noticing features. For example, in a bike, if you convolve, you might be able to notice the shape of a handlebar and basically recognize that as a key feature of a bike. And recurrent neural networks basically let you recur in terms of feeding data in. So if you combine these two, you can create video analysis using an RCNN, so a recurrent convolutional neural network. And so these architectures are really powerful because you can create combinations that let you do various tasks. And lastly, speed and memory optimization is something that's really important when working with big datasets, large networks, and very rigorous and complicated calculations and operations, which are all required in neural networks. So even though right now our data is really small, you can see that as soon as we get even remotely larger for MNIST, for example, our dataset is large, and so is our neural network. Our neural network now had more than 100,000 weights. So that means there's a lot more calculation that has to go on behind the scenes, and a lot more memory has to be used. So all of these are important things to consider while doing NN2, and yeah, that's my presentation. Thank you guys.